Mars looks pretty dead from space, a rusty desert with toxic soil and killer radiation that would fry anything alive in minutes. But here's the wild part. Everything interesting about Mars might actually be underground, completely hidden from our cameras and rovers. While Curiosity's been taking selfies in the dust, NASA's InSight probe detected something weird, marsquakes coming from deep caverns we can't see. Think about it. Earth has massive underground caves, water systems, and even entire ecosystems that never see sunlight. Mars is actually perfect for underground spaces. Lower gravity means caves can be way bigger without collapsing, and its crust is thick and stable. The surface of Mars is basically uninhabitable, but underground? That's where you'd want to be if you were trying to survive there. We found entrances to lava tubes on Mars that could fit entire cities, and radar data shows huge spaces under the polar ice caps. The real kicker is that we've only mapped about 0.1% of what's under Mars's surface. That's like judging Earth by looking at a parking lot. Our rovers are amazing, but they're just scratching the surface, literally, of what could be the biggest discovery in human history, lurking just a few kilometers down. So, what exactly makes Mars's underground so special? For starters, its core cooled way faster than Earth's, creating unique geological conditions we're just beginning to understand. Those marsquakes InSight detected? They hint at massive chambers that could stretch for kilometers, potentially filled with trapped ancient atmosphere or even liquid water. The science gets wild when you consider Mars's past. It once had a magnetic field and oceans, but something catastrophic made it lose both. We'll dig into hard evidence about these underground spaces, from satellite radar data to mineral analysis that suggests extensive water networks below the surface. Here's the really mind-bending part. If any life evolved on Mars during its wet period, going underground wouldn't just be possible. It might have been the only way to survive. The math checks out, too. Mars's lower gravity and stable crust could support massive artificial structures, theoretically big enough to house entire civilizations. We'll break down exactly what technology would be needed to survive underground on Mars and compare it to capabilities we've seen in other extreme environments. Most importantly, we'll explore why our current exploration methods might be completely missing signs of past or present activity beneath the surface. Size plays a massive role in planetary cooling. Mars being half Earth's diameter means it lost heat way faster, like how a shot of espresso cools quicker than your morning coffee. The physics is pretty straightforward. Mars has a much larger surface area compared to its volume, which means more heat escapes into space relative to its total heat content. InSight's data showed something fascinating. Mars's core is basically a cold, solid chunk of metal, unlike Earth's churning liquid core that powers our magnetic field. Without that internal heat engine, Mars can't generate the protective magnetic bubble that shields Earth from deadly solar radiation. This rapid cooling had a domino effect. As the core solidified, Mars lost its ability to recycle minerals through plate tectonics, making its crust extra thick and stable. The timing was brutal. Mars's core probably solidified within its first billion years, right when life might have been trying to get started. But here's where it gets interesting. That stable, thick crust actually makes Mars perfect for maintaining large underground spaces without collapse. Recent seismic data suggests there might still be some liquid elements in Mars's core, just not enough to generate a meaningful magnetic field. Some conspiracy theorists claim Mars is hollow, but basic physics makes that about as likely as finding a McDonald's on Olympus Mons. A planet-sized hollow sphere would instantly implode. Gravity doesn't just pull down, it pulls everything toward the center from all directions. InSight's seismometer caught marsquakes bouncing through different layers of the planet, mapping out density changes that match exactly what we'd expect from a solid planet. The way these quakes travel tells us Mars has distinct layers, a crust, mantle, and core, each with their own specific density signature. We can actually calculate Mars's moment of inertia, basically how mass is distributed inside it, and it matches perfectly with a solid planet, not a hollow shell. The gravity field around Mars, measured by orbiting satellites, shows mass concentrations that could only exist in a solid planet. If Mars were hollow, its outer shell would need to be impossibly dense to match its observed mass. We're talking denser than a neutron star. The real story of what's inside Mars, with its complex layers and partially molten core, is way more interesting than any hollow planet theory. When seismic waves hit Mars's core, they bounce around like a ping-pong ball, giving us a natural ultrasound of the planet's guts. These waves travel at different speeds through various materials. Think of how sound moves differently through air versus water. InSight picked up waves that suddenly slowed down about 1,830 kilometers deep, exactly where the planet's metal core begins. The speed and pattern of these waves proved something crucial. Mars's core is mostly solid metal, with maybe just a thin outer layer that's still molten. By tracking multiple marsquakes, scientists built a 3D map of the core's properties. Turns out it's mostly iron and nickel, with a dash of lighter elements like sulfur. The core's solid state explains why Mars lost its magnetic field. Without liquid metal sloshing around, there's no dynamo effect to generate magnetism. Comparing Mars's core to Earth's is like comparing a frozen meatball to hot soup. Earth's core is still mostly liquid and churning. This solid core discovery rewrites our understanding of how quickly planets can cool down and lose their protective magnetic shields. While Mars's core might be frozen solid, its crust tells a completely different story. It's riddled with massive underground spaces. Orbital scans of Arsia Mons revealed lava tube entrances wider than a football field. We're talking caves that could swallow entire city blocks. Mars's gravity is just 38% of Earth's, which means these caves can grow 3 times larger without collapsing compared to similar structures on our planet. Satellite radar spotted hundreds of these pit craters, basically natural skylights where cave roofs have collapsed, giving us a peek at the tunnels below. The largest known lava tube on Earth, in Hawaii, could fit a Boeing 747, but the ones we've found on Mars could host an entire airport terminal. These Martian caves aren't just empty tubes. Many show signs of mineral deposits that suggest they once held flowing water. Ground-penetrating radar from Mars orbiters hints at networks of connected chambers that could stretch for dozens of kilometers. The stable crust means these caverns have likely remained intact for billions of years, potentially preserving evidence of Mars's wetter past. Some of these chambers might still contain pockets of ancient atmosphere or even frozen water deposits, trapped since Mars's warmer days. Volcanic activity on Mars created these lava tubes in a pretty straightforward way. Molten rock flows beneath a cooled crust, then drains out, leaving behind massive tunnels. The Seven Sisters, a series of pits on Arsia Mons, aren't just random holes. They're the exposed entrances to a massive underground highway system carved by ancient lava. Each of these Martian lava tubes could theoretically stretch up to 40 kilometers long. That's like having an underground tunnel running the length of Manhattan. Beyond volcanic caves, Mars likely has solution caves formed by dissolving minerals, just like Earth's limestone caverns, but potentially much bigger. Ice sublimation, when frozen CO2 or water ice turns directly into gas, might have hollowed out huge chambers near the poles. The combination of low gravity and thick crust means these caves could be incredibly stable. Some calculations suggest they could span up to 5 kilometers across without structural support. Recent thermal imaging shows temperature differences at cave entrances that hint at vast networks extending far beyond what we can see from orbit. Some of these caves might connect to deep aquifers, underground water reservoirs that could still exist today, protected from surface radiation and extreme temperature swings. The real game changer is how these different cave types might interconnect. Imagine a natural underground subway system linking volcanic tubes to water-carved caverns. The evidence for Mars's underground spaces isn't just theoretical. We've got high-res photos of massive pit chains in Noctis Labyrinthus that look like someone took bites out of the planet's surface. Mars Reconnaissance Orbiter's HiRISE camera caught something wild, perfectly circular holes called skylights that drop into darkness with no visible bottom in the images. These features aren't random. They follow clear patterns along fault lines and ancient volcanic regions, suggesting they're part of larger underground networks. Noctis labyrinthus, a maze-like system of intersecting valleys, shows clear signs of ceiling collapse. Imagine the Grand Canyon, but caused by cave-ins rather than river erosion. Infrared imaging reveals these holes maintain steady temperatures despite Mars's extreme day-night swings, suggesting they connect to extensive underground systems that regulate their climate. The spacing and size of collapse features follow mathematical patterns that match what we'd expect from naturally forming cave networks, just scaled up due to Mars's lower gravity. Ground-penetrating radar picked up void signatures that extend kilometers deep, way bigger than what we see from the surface collapses. Some of these holes show seasonal changes in appearance, hinting at active processes still happening in the caves below. The really compelling evidence comes from comparing these features to Earth's volcanic regions. The patterns are nearly identical, just supersized on Mars. While Earth's crust is like a jigsaw puzzle in constant motion, Mars's surface hasn't moved much in billions of years. It's basically frozen in place. This geological stability is a massive advantage for underground structures. Imagine building a house on solid bedrock versus shifting sand. Earth gets around 20,000 measurable earthquakes yearly, but Mars only experiences tiny tremors, mostly from meteor impacts and thermal changes. The red planet's crust is also way thicker than Earth's, about 50 kilometers on average compared to our 30, creating a super stable shell. Any underground structures, natural or artificial, would face almost zero risk of collapse from tectonic movement. They just sit there, unchanged, for millions of years. Mars's single-plate structure means no volcanic activity to pump toxic gases into cave systems, unlike Earth where underground spaces often fill with dangerous fumes. The stable crust also prevents groundwater movement that could flood chambers, a common problem in Earth's cave systems. This geological deadlock creates perfect conditions for long-term underground habitation. You could build massive structures without worrying about them getting crushed. The few marsquakes we've detected are so weak they wouldn't even knock over a coffee cup. Nothing like Earth's building-toppling tremors. These Martian caves aren't just empty spaces. They're potential atmospheric time capsules that might still hold pockets of ancient Mars's thicker atmosphere. The physics is fascinating. Cold cave walls can actually trap and freeze water vapor, creating hidden deposits of ice that could survive for millions of years. Recent studies found that some Martian cave entrances show frost accumulation patterns that shouldn't exist at those latitudes. Something weird is happening in there. The temperature difference between cave interiors and the surface creates air currents that could concentrate water vapor and CO2, similar to how Earth's caves trap radon gas. Lab experiments simulating Martian cave conditions show that even in the current thin atmosphere, water ice could build up in protected corners and crevices. The pressure inside deep caves might be significantly higher than the surface. Not enough to walk around without a suit, but enough to make water exist as a liquid. Some caves might connect to underground aquifers, creating localized humid environments where specialized microorganisms could theoretically survive. The real kicker is that these caves could preserve samples of Mars's atmosphere from different geological periods, like a natural time capsule of the planet's climate history. Thermal imaging shows some cave systems maintain temperatures around -23°C year-round, cold by Earth standards, but practically tropical for Mars. Living underground on Mars isn't just a cool sci-fi concept, it's probably the only practical way to survive there long-term. The numbers are wild. Surface radiation on Mars hits about 250 millisievert per year. That's like getting 250 chest X-rays annually, enough to significantly increase cancer risk. Just 3 meters of Martian rock cuts radiation exposure by 99%, instantly solving one of the biggest challenges of Mars colonization. Underground spaces naturally maintain temperatures around -5 degrees Celsius, while the surface swings between a brutal +20 degrees Celsius to -140 degrees Celsius daily. Mars gets peppered by about 200 metric tons of micrometeorites every day. Underground structures wouldn't need expensive impact shielding. The soil above these caves contains hydrogen-rich compounds that not only block radiation but could be processed into rocket fuel or water. Unlike Earth's caves, which often flood or fill with toxic gases, Martian caves are remarkably stable due to the planet's geological inactivity. The constant darkness isn't actually a problem. We already have LED technology efficient enough to grow food underground using minimal power. Some calculations suggest a nuclear reactor the size of a hot tub could power an underground colony of 100 people indefinitely. Deep underground, Mars isn't the dead zone you might expect. Models show there's still enough residual heat at 5 to 6 kilometers down to keep water liquid. The planet's core might be cold, but radioactive decay in the crust generates a tiny bit of warmth, about 1/10 of Earth's geothermal heat. This weak heat flow creates a Goldilocks zone where temperature and pressure hit the sweet spot for liquid water, despite Mars's thin atmosphere. Rock pressure at those depths generates around 50 atmospheres, enough to prevent water from instantly boiling away in Mars's low-pressure environment. The geology gets interesting here. Certain minerals found in Martian meteorites suggest they formed in warm, wet underground environments relatively recently. While Mars's magnetic field fizzled out billions of years ago, deep caves provide better radiation protection than any magnetic shield could. The math is pretty wild. Earth's magnetic field cuts cosmic radiation by about 50%, but just 2 meters of Martian rock blocks 99.9% of it. These underground radiation shelters might explain why we keep finding organic molecules in Martian soil. They could have been preserved there for billions of years. Recent data suggests some of these deep aquifers might be kept liquid by dissolved salts, which can lower water's freezing point by up to 40 degrees Celsius. Deep impact craters have exposed layers of clay minerals that could only form through long-term contact with liquid water, suggesting vast underground reservoirs. Spectral analysis of these hydrated minerals shows they're remarkably well preserved. They would have broken down if exposed to surface conditions, meaning they formed underground. Life without sunlight isn't as impossible as you might think. Earth's deep-sea vents support entire ecosystems running on chemical energy instead of photosynthesis. Martian underground creatures could tap into chemical reactions like serpentinization, where minerals react with water to produce hydrogen, basically free energy. The process is surprisingly efficient. A cubic meter of serpentinizing rock can generate enough hydrogen to support thousands of microorganisms. These chemical-eating microbes could form thick mats, similar to the white bacterial carpets found around Earth's hydrothermal vents. Larger organisms could evolve to graze on these microbial colonies, creating a food chain completely independent of surface conditions. Mars's underground lakes might host ecosystems similar to those in Earth's deep aquifers, where bacteria metabolize minerals like iron and sulfur. Some Earth microbes can switch between different energy sources depending on what's available. Martian life might be even more adaptable. The real game changer would be if Martian life figured out how to harness radioactive decay for energy, something we've found bacteria doing in Earth's uranium deposits. Recent lab experiments show that some Earth bacteria can survive on just hydrogen and CO2, both of which are abundant in Mars's underground spaces. Deep underground on Earth, microbes pull off an incredible trick. They split water molecules using radioactive particles, creating free hydrogen for energy. Scientists estimate that nearly half of Earth's biomass exists in the deep biosphere, a vast underground ecosystem we barely understand. These underground organisms are incredibly efficient. Some can survive on just a few molecules of food per year, basically running in ultra-low power mode. The diversity is mind-blowing. Researchers have found bacteria thriving 3 miles underground, feeding on everything from hydrogen to radioactive waste. Mars's underground could host similar life forms, but with even cooler adaptations, like organisms that can switch between multiple chemical food sources as conditions change. Some Earth bacteria use quantum tunneling to extract electrons from minerals, basically stealing energy at the atomic level. The pressure in Mars's deep caves could create supercritical CO2, a weird state of matter that some Earth microbes actually prefer to live in. Underground Martian life might evolve to be incredibly energy efficient, possibly surviving on power levels thousands of times lower than Earth's most frugal bacteria. These organisms could form complex networks, sharing resources and energy through chemical signals, like a living internet running through Mars's crust. An underground Martian civilization would leak telltale signs. Physics makes it basically impossible to hide a city-sized heat signature. Our thermal cameras can spot temperature differences of 0.1 degrees Celsius from orbit. Even deep underground settlements would create detectable hotspots through heat dissipation. Any technology using nuclear power would release trace amounts of xenon gas, which our instruments could detect even in Mars's thin atmosphere. Large-scale underground farming would pump out methane and other biological gases in patterns very different from natural geological sources. Electromagnetic emissions are another giveaway. Any advanced technology would create detectable radio signals, even if they're trying to stay hidden. Current Mars orbiters carry magnetometers sensitive enough to detect artificial magnetic fields from power generation or electromagnetic tech. Regular patterns in ground deformation could reveal underground construction. Even subtle surface changes show up in high-resolution radar mapping. Waste heat management would require vents or radiators. These would create distinctive infrared signatures, different from natural geological features. The real challenge isn't detecting these signs, it's distinguishing them from Mars's natural geological processes, which can mimic artificial signatures. Our current Mars rovers are like kids playing in a sandbox while the real action happens deep in the basement. They can only drill about 7 centimeters into the surface. The harsh UV radiation and oxidizing chemicals in Mars's soil destroy organic molecules within centimeters of the surface, creating a death zone for any biological evidence. We're basically looking for life in the worst possible place. It's like trying to find fish by searching in the Sahara Desert instead of the ocean. NASA's planetary protection rules actually prevent us from exploring the most promising sites. We can't risk contaminating potential habitats with Earth microbes. The real search for life requires drilling kilometers deep, but our heaviest rover weighs less than a small car, not exactly equipped for serious mining operations. Current drilling tech on Mars is so limited that we've explored less than 0.001% of the potential habitable zone beneath the surface. The few samples we've analyzed come from the most heavily sterilized layer of Mars. Imagine judging Earth's biodiversity by studying only sun-bleached rocks. Future missions will need completely new drilling technologies. Current methods would take decades to reach depths where life might actually exist. The most promising sites for subsurface life are often the most dangerous for rovers to explore. Steep slopes near cave entrances or unstable ground above lava tubes. If an advanced civilization exists on Mars today, they're pulling off the galaxy's greatest hide-and-seek game. Our thermal sensors haven't detected any unusual heat clusters that would indicate large settlements. A city of even 10,000 people would generate enough waste heat to show up as a thermal anomaly on our infrared maps, even if it was kilometers underground. The Mars Reconnaissance Orbiter's ground-penetrating radar should have picked up any large artificial structures or unusual geometric patterns in the subsurface. While a small group of survivors might theoretically hide in deep caves, maintaining a technological civilization would require infrastructure that's impossible to completely conceal. Our radio telescopes are sensitive enough to pick up a cell phone signal from Mars, yet we've detected no artificial electromagnetic emissions. The power requirements for an underground city would be massive. Even nuclear reactors would leave isotopic signatures in the atmosphere that we could detect from Earth. Any large-scale agriculture or industry would alter local mineral concentrations and create chemical signatures that would stand out from natural geological processes. The one scenario that can't be completely ruled out is a post-technological civilization that's gone into extreme minimalism, basically living like bacteria in deep caves. But maintaining genetic diversity and technological knowledge across generations would require a population of at least several thousand, making complete concealment nearly impossible. Building an underground Mars base isn't just about digging holes. You'd need some seriously clever tech to avoid suffocating in your own carbon dioxide. The math shows you'd need about 30 cubic meters of actively managed airspace per person, with mechanical systems that can process out CO2 faster than humans produce it. Artificial photosynthesis using metal organic frameworks could recycle CO2 back into oxygen about 100 times more efficiently than plants. For water, you'd want plasma drills that can melt through ice deposits while simultaneously sterilizing the water, way more practical than hauling it from Earth. The most efficient power setup would be a mix of small nuclear reactors and supercritical CO2 turbines, which work better in Mars's atmosphere than traditional steam engines. Sealing off cave sections would require some wild materials science. Think self-healing polymers that can automatically patch microcracks from pressure changes. The killer app would be bioengineered extremophile bacteria that can extract metals from Martian rocks while producing oxygen as a waste product. 3D printing with Martian regolith could create radiation shielding structures, but you'd need specialized binders that can cure in near-vacuum conditions. The trickiest part isn't the individual systems, it's making them work together in a closed loop where nothing gets wasted and everything gets recycled. The timing of Mars's climate collapse matches perfectly with when theoretical civilizations would have needed to make a critical choice: adapt or die. Around 3.5 billion years ago, Mars lost its magnetic field, letting solar radiation strip away its atmosphere like a cosmic vacuum cleaner. Any surface-dwelling species would have watched their world transform into a freezing desert within just a few thousand years. Plenty of time to plan and execute an underground migration. Geological evidence shows this wasn't a gradual decline. Mars got hit with massive solar storms that would have made the surface increasingly lethal. Moving underground wouldn't just be about survival. The stable temperatures and protection from radiation would make it easier to maintain advanced technology. Cave systems that formed during Mars's volcanic period would have been prime real estate, ready-made shelters with natural insulation and potential water sources. The polar regions might have been the last habitable surface zones, explaining why we see complex networks of caves and tunnels near Mars's ice caps. Any civilization making this transition would have needed to master energy production first. You can't farm sunlight in a cave. The underground shift might explain why we don't see obvious ruins on the surface. Everything important would have been relocated below during the migration. The methane plumes detected by Mars orbiters are particularly weird. They appear and disappear seasonally, exactly like biological emissions on Earth. Deep impact craters have exposed layers of clay minerals that could only form through long-term contact with liquid water, suggesting vast underground reservoirs. Spectral analysis of these hydrated minerals shows they're remarkably well preserved. They would have broken down if exposed to surface conditions, meaning they formed underground. Some Martian meteorites contain tiny magnetite crystals identical to those produced by Earth bacteria, though we can't rule out chemical processes. Concentrated deposits of specific minerals like jarosite appear in patterns that, on Earth, are typically created by microbial colonies. The distribution of hydrogen-rich compounds detected by orbital neutron spectrometers suggests networks of buried ice or liquid water far more extensive than surface features indicate. Certain crater walls show periodic dark streaks that appear during warm seasons, possibly liquid water seeping from underground reservoirs. The chemical composition of some deep cave sediments contains organic molecules that are surprisingly complex for purely geological processes. Radar scans reveal layered deposits under the poles that don't match what we'd expect from natural ice formation, hinting at possible artificial structures. The Borealis impact basin covers 40% of Mars's surface. An asteroid hit so massive it could have sterilized everything above ground while paradoxically creating new underground shelters. Impact simulations show that while surface temperatures would have hit thousands of degrees, deep caves actually got compressed and strengthened by the shock waves. The heat pulse from major impacts would have melted subsurface ice, potentially creating temporary underground oceans where life could ride out the chaos. We see this pattern on Earth. Species that survived the dinosaur-killing impact were mostly burrowers, cave dwellers, and deep-sea organisms. Each major impact would have driven surviving organisms deeper, naturally selecting for traits that work well underground, like low energy needs and chemical sensing. The impacts didn't just destroy, they created networks of fractured rock that could have served as ready-made habitats filled with impact-melted water. Analysis of Martian meteorites shows evidence of multiple sterilizing impacts, but only in surface layers. Deeper materials preserved signs of potential biological activity. The timing of Mars's biggest impacts lines up suspiciously well with changes in atmospheric chemistry that could indicate life adapting to subsurface environments. Recent studies suggest impacts might have actually concentrated organic compounds in underground spaces, creating pockets of chemical ingredients needed for life. Radar scans from ESA's Mars Express found something wild in 2018, a lake of liquid water bigger than Paris sitting 1.5 kilometers under Mars's south pole. The water stays liquid despite temperatures around -68 degrees Celsius because it's super salty. Like antifreeze, salt lowers water's freezing point dramatically. Pressure from the ice cap above creates a liquid sandwich effect, squeezing the water until it has no choice but to stay liquid, even in Mars's brutal cold. Computer models suggest these aren't just isolated pools. Networks of underground waterways could connect various liquid reservoirs across thousands of kilometers. The physics works out perfectly. At depths between 6 and 8 kilometers, pressure and residual heat from Mars's crust create conditions where liquid water is stable. These deep aquifers wouldn't be like Earth's freshwater. They'd be more like the super salty lakes under Antarctica, where extreme-loving microbes thrive. Recent gravity measurements hint at massive water deposits hiding in Mars's crust, enough to cover the entire planet in a 40-meter deep ocean if brought to the surface. The real game changer is that these water bodies are probably still active today. We've spotted seasonal changes in radar signatures suggesting water movement. Some of these underground reservoirs might tap into ancient water systems that have been cycling liquid continuously since Mars was warm and wet billions of years ago. Our deepest physical probe into Mars barely scratched 5 centimeters. Imagine trying to understand Earth by only studying the paint on your house. Ground-penetrating radar from Marsis can peer about 5 kilometers down, but it's like looking at a blurry ultrasound. We can spot big features but miss the details. InSight's mole probe was supposed to dig 5 meters down, but got stuck at 60 centimeters because Mars's soil behaved completely differently than expected. We've mapped less than 0.01% of Mars's potential habitable zone. That's like trying to understand New York City by only exploring one block of Manhattan. The deepest natural windows we have into Mars's subsurface are impact craters, which can expose layers up to 7 kilometers deep. China's Tianwen-2 mission plans to drill 100 meters down. That's 20 times deeper than anything we've tried before, but still just scratching the surface. Seismic waves from marsquakes give us indirect data about depths up to 800 kilometers. But it's like trying to understand a building's layout just by tapping on the walls. The real challenge isn't just drilling deeper, it's keeping instruments working in conditions that can destroy electronics within minutes. Future missions might use plasma drills that melt through rock while creating their own protective tunnel lining, potentially reaching depths of several kilometers. The most compelling evidence for Mars's underground spaces comes from weird surface features that look like someone took giant cookie-cutter bites out of the planet. High-rise cameras spotted chains of perfectly circular holes called pit craters that drop into pure darkness. Some are over 100 meters wide and show no bottom in our highest resolution images. Chaos terrain, areas where the surface has completely collapsed into jumbled blocks, suggests massive caverns underneath that emptied out and caved in. These collapse zones follow mathematical patterns that match cave formation on Earth, just scaled up due to Mars's lower gravity. Infrared cameras caught something fascinating. Many of these holes maintain steady temperatures despite Mars's extreme temperature swings, suggesting they connect to climate-controlled spaces below. The Cerberus fossae region shows fresh crack systems that could be actively forming today, with some fissures wide enough to swallow a house. Satellite radar detected void signatures extending several kilometers deep under these surface features, way bigger than what we can see from above. Some pit chains show seasonal changes in appearance, with frost patterns that suggest airflow between the surface and whatever's hiding below. The spacing between collapse features follows precise mathematical ratios that match how cave networks naturally develop. It's like nature's architectural blueprint. Our search for hidden Martian cities faces a brutal numbers problem. We've only explored about 0.0001% of the potentially habitable underground volume, equivalent to checking a single house to find someone hiding in New York City. Ground-penetrating radar can't distinguish artificial structures from natural caves. Once you go deeper than about 10 meters, a city could be sitting right under our rovers and we'd miss it completely. Small, energy-efficient habitats using geothermal power would be basically invisible to our thermal sensors, especially if they're built inside existing cave networks. The depth problem is mind-boggling. Mars's crust is 50 kilometers thick, and we've only peaked at the first few meters. A civilization using advanced materials could mask their heat signature by spreading it out over a large area, making it indistinguishable from natural geological warming. Current Mars orbiters can't detect electromagnetic signals from deeper than about 200 meters. Any shielded communications would be completely invisible to us. The real kicker is scale. A self-sustaining habitat for 10,000 people would only need about 1 cubic kilometer of space, literally a needle in Mars's planetary haystack. Our best instruments could miss entire underground industrial complexes if they're built from local materials and properly insulated. The time factor matters too. We've only been seriously looking for about 20 years, while any hidden civilization has had millions of years to perfect their concealment. Future Mars missions are about to get wild. The European Space Agency is developing snake-like robots that can slither through narrow cave entrances and map entire underground networks autonomously. NASA's Braille project is testing AI systems that can identify biological signatures in cave minerals, basically teaching robots to think like geologists. The coolest tech coming up is probably JPL's Nebula platform. Imagine a swarm of drones that can map pitch-black caves in 3D while searching for signs of life. Japan's planning something crazy, a drill that uses superheated plasma to melt through rock while creating a reinforced glass tunnel behind it, potentially reaching depths of 100+ meters. China's Tianwen-3 mission might include mother-daughter rovers, small deployable bots that can rappel down into crater pits while staying connected to the main rover. The real game changer will be NASA's subsurface water ice mapping project, SWIM, using combined data from multiple orbiters to find underground ice deposits perfect for future bases. Some proposed missions would use seismic charges to map huge underground areas, like ultrasound for an entire region of Mars. Engineers are working on self-healing drill bits made of memory metals that can change shape when they hit different rock layers, preventing the problems that stopped previous drilling attempts. The craziest proposal is probably the Mars Mole concept, a nuclear-powered tunneling probe that could theoretically drill 10 kilometers deep while beaming data back through the rock. After diving through all this evidence, we're left with a fascinating puzzle. Mars's underground is way more complex than anyone imagined even a decade ago. The science is solid on several points. Mars has a frozen core that cooled super fast, creating unique conditions for massive cave systems that could stretch for kilometers. These aren't just empty holes. They're potentially habitable environments shielded from radiation, with stable temperatures and possible access to liquid water. The real breakthrough is understanding how these spaces formed. A perfect storm of low gravity, thick crust, and ancient volcanic activity created caverns that could dwarf anything on Earth. While we haven't found any alien cities, the math shows that underground habitats are not just possible, but actually practical. The physics and engineering check out completely. The most mind-bending part? We've barely started looking. Our best instruments have explored less than 0.001% of Mars's potentially habitable underground volume. Current evidence points more towards simple life forms, think bacteria thriving in deep aquifers, than advanced civilizations. But we're just beginning to develop tech that can actually test these theories. The combination of new radar data, seismic measurements, and mineral analysis paints a picture of a planet with vast networks of interconnected underground spaces that could host all sorts of surprises. Here's the kicker. Every new Mars mission reveals more complexity in these subsurface systems, suggesting we're just scratching the surface of what might be the biggest discovery in human history. Looking at Mars today, we see a world of endless possibilities hidden just beneath our feet. A planet that might harbor more secrets than we ever imagined. The next decade of Mars exploration will deploy technologies that sound like science fiction. Plasma drills, cave diving drones, and swarms of autonomous robots mapping vast underground networks. Each new mission peels back another layer of Mars's complexity, revealing a world that's far more dynamic and potentially life-friendly than its dusty surface suggests. The real revolution isn't just finding caves or water. It's understanding that Mars's underground could be the perfect refuge for life, shielded from the harsh realities above. We're standing at the edge of a new era in Mars exploration, where the question isn't just, was there ever life on Mars, but what kind of life might still exist there today? The technology we're developing to explore Mars's depths will revolutionize how we search for life throughout the solar system, from Europa's ice-covered oceans to Titan's methane lakes. As we push deeper into Mars's subsurface, we're not just exploring another planet, we're potentially uncovering the greatest scientific discovery in human history. The next time you look up at that red dot in the night sky, remember, Mars isn't just another desert world. It's a planet of underground wonders waiting to be discovered.